is the great unconformity spot. Here is your Precambrian, the crystalline basement. In this case, this is a schist. You can tell because it has all these very fine, this very fine platey look to it. It's called foliation. And that's all created by the pressure that was squeezing this, getting all the long axes of the crystals to line up. You can actually see the little reflective mica bits. If you come up and look at it, all those little pieces of muscovite, they're all aligned in a row. So this rock, 1.7 billion years ago. Up here I'm sitting on the Tapete sandstone, 500 something million years ago. So you basically got over 1 billion years of missing time running right down this line here. Contact, you've seen it from the boat, now you can come up and actually touch it. The thing isn't in the, there's nothing there. It's missing time is the unconformity, this line. And we can generally treat this line as a single moment in geologic time. So at one point in time, this was the surface of the planet. And as you might expect, it's not exactly level. If you look behind you or look here, notice that this line comes up from the ground, kind of peels back in, up and down. Along the boat, when we were on the river, you can see these big piles of this black rock, and they sit up high, and the peat sandstone would be lying around it. So we have what we call paleotopography, ancient land surface. So we had that mountain building event that made these schists and gneisses. Then we had the erosion of those down to a relatively flat surface. Then we had all that Grand Canyon supergroup rock. We were standing with the Bass limestone earlier today. That's all laid down on top. And that stuff got faulted and tipped into those blocks, and all that got sheared off pretty nice and flat. So that faulting occurred that originally tipped those blocks of Grand Canyon supergroup about 800 million years ago, give or take, during a breakup of a supercontinent that was called Rodinia. That supercontinent broke up. Eugenie is only the most recent supercontinent. Every 500 million years or so, the Earth makes a supercontinent, takes it back apart, puts it back together, and takes it back apart. They call that 500 million year cycle of supercontinent to supercontinent, the Wilson cycle, after Tuzo Wilson, who is sort of the father, the person who then finally formulates plate tectonics with all the data that's being discovered by people post-Wegener. So they had a supercontinent called Rodinia. That supercontinent broke up. What was sort of odd about that supercontinent? It broke up. It was on the equator. So you ended up with a whole lot of little continents all floating around the equator. This had rather significant effects on the Earth's climate, because what you had then was a bunch of little continents sitting around the equator. There was no ocean circulation to the equator. The ocean kept having to circulate off the poles. Made the ocean rather cold. Plus, before that time period, you had all those cyanobacteria making oxygen, pulling CO2 out of the atmosphere. Opposite situation of what we have today, right? You get more CO2, things get warmer. You have less CO2, things get cooler. So you had global cooling caused by oxygen pollution, followed by, going on at the same time, you had supercontinents stuck around the equator, which was cooling the oceans even more. So you started to build polar ice on the poles, floating out there in the ocean, and that ice reflects sun back, has a high albedo, so it reflects most of the light back into space. So that keeps cooling the Earth even more. And you start growing glaciers on these little continents, even though they're close to the equator, they still have high points, and you start to grow glaciers on them. Eventually you reach a tipping point, what they refer to as ice albedo runaway, where the effect of the continuing growing ice fosters more growing ice, and pretty soon you get the planet pretty much frozen over. Now, by us. Then you go through a period, what they call the snowball Earth, where things are getting hotter, or basically being cold, and then they kind of tip through warm cycles and kind of break some of the ice up, and you get cold again. But the Earth stays glaciated or super glaciated for about 100 million years, give or take.
Does that happen with each of these cycles, these 500 or half billion year cycles, or when it did that?
It happened with this particular cycle. Though with our current cycle, we got real close about 100,000 years ago.
You might mention that the reason why these continents move around is because the inside of the Earth in various places is very hot, and hot air rises, so does magma, and that moves the continents around. So we would have been toast, we wouldn't have been at all, if there hadn't been a warm core for the Earth during the snowball Earth freeze.
Well, that's an
The
even
continents
deeper.
the continents kept moving.
Yeah, the continents keep
And
moving.
that helped. That helped.
And the continents keep moving, and that has two factors. One, of course, as the continents move, volcanism is going on. Volcanism is releasing, volcanoes release a heck of a lot of CO2. So the volcanoes are pumping CO2 back into the atmosphere because the Earth is so cold and life is stuck hiding in hydrothermal vents. You know, they're not taking it back out. So you start to get them up, you start to build up CO2 in the atmosphere. Plus the continents start to move away from the equator. And with them moving away from the equator, the ocean starts to get to cycle up to the equator. So you start to get warm ocean water pooling around the equator, so you get a circumequatorial current. That keeps the oceans much warmer than they do when you can't get to the equator. You have to cycle off to the poles and eventually break out of this cycle at about 600 million years or so ago. And that's about when you start getting to deplete sandstone. All these glaciers melt finally, oceans start to rise. In that 500 and something million year range, oceans start encroaching on land in some of these areas of land. We talked about transgression, so this is the beginning of our Cambrian transgression. We see this pretty much globally. You have this nice contact, Precambrian rocks, they're all pretty sheared off, relatively flat, and then about in the 500 million years ago, 600 million year range, and you start to see this rise, general rise in ocean levels as these old continents are sitting low and subsiding. They've pretty much been ground off by the glaciers to boot. So you got formation, there's plenty of sediment around, you start to deposit here, sediment on top. So it starts out the waves are lapping, this little ocean comes in, and what you have are little ancient shoals and topographic highs along these ancient islands as this sea comes in. In fact, further down the river there's a giant island in the record that actually cuts all the way up into Muav with a huge pile of granite. The harder stuff, the schist is relatively soft, it chemically weathers easily. You can actually see it along the contact by little micrograins of vent. This stuff will break down pretty easily into clays and wash away. And then running through it, you have these bigger bits from those veins that you saw, the pink granite coming up through it. And that stuff's mostly quartz and feldspar. They're going to be more resistant to weathering. You see those bits. What we have here in these sand layers, these conglomeratic layers, are actually pieces of that pink granite that have been mobilized by weathering away the schist. That stuff's rolling around in this ocean in storms. And if you notice, see how big the chunks are down here? Move up to the next level, those chunks are a little bit smaller, a little smaller up there, little tiny pebbles. Pretty soon it's just this sort of pinkish colored clayey sand. Then you get further up and it's all just pure silica sand. You've eliminated, you're no longer exposing any of this ancient Precambrian rock to weathering anymore. Other neat features that you can see here. Notice, remember when we were up in the Coconino, we talked about cross beds. You can see some cross beds right here, coming across like this. But notice these cross beds don't look like those Coconino cross beds in Esperanza. They were very vertical, they had a much high angle, very straight, what we would call very tabular. These are kind of what we would call troughy. Notice they kind of have a little S-bend. They kind of curve down, curve flat, curve down, and curve flat. Smaller scale too, right? This cross bed's 10, 15 centimeters high compared to those 40, 50 multi-meter, 10, 20 meter scale ones we saw above. That's really indicative that these are cross beds laid down by water. So here what you have is a little sandbar forming on this shoal. If you've been watching as we've been going along the river offshore, all those beaches, those bars that are forming. Notice as you look across the top of the bars, there are those ripples. You spend some time watching, you know, as the water washes over it, picks up some of the sand, drops it on the shoreline side. If we went down to one of those drain bars now, and I took out the shovel and we dug perpendicular to it, you'd see a series of parallel trough cross beds as that bar migrates onshore or migrates offshore. You have a lot of these small scale features. So you got your ancient rock down here, 1.7 billion. You have your what we frequently call a basal conglomerate. This is made out of the harder to weather chunks that are weathering out from, say, this area here, and actually there's some higher. When we're done, we'll walk up Blacktail, take the angle turn, walk up this even bigger one of these islands. But these things are washing around. They're relatively angular down here, and that means they haven't been exposed to getting tossed around for very long, haven't been transported far. The more sediment is transported, the smaller the chunks get, and the rounder they get. Because you'll look, chunks are smaller, and they're getting rounder as you move up in time. So it increases the length of time that you have open to physical weathering. Physical weathering makes big rocks into little rocks. Chemical weathering makes rocks into different kinds of things. So the mica becomes the clay, the quartz and the feldspar, mostly in this case it's quartz. The most resistant mineral there is to weathering, lasts the longest. That's why you go to a nice beach, it's all silica sand, all nice white shiny beaches, because it holds up the longest. It can make it all the way out of river system. While you look at river sand, look at the Colorado, there's quartz sand, there's mica flakes, there's hornblende, there's a whole bunch of less stable minerals and a lot of clay. So you get down the winnowing, you have this nice silica sand. That's what makes up the Tepete sandstone. In fact, all around the planet, the base of the Cambrian, you have silica sand. You go up to Wisconsin, silica sand is where they go mining all the frac sand up in Wisconsin and Minnesota. It's all Cambrian sandstone. No life going on land to mess up sedimentary systems. It's all coming to the ocean. Plants really also kind of screwed up the whole nature of sedimentation with their annoying roots and chemical weathering capabilities. But this is just pure physical and chemical weathering, nothing getting in the way. Carries it all down to the ocean. So you have what's called the sand conveyor belt. All over the world, Cambrian pretty much has this kind of probably glacially generated contact, and then a lot of silica sand on top. One other thing is important if you think about those dates. Snowball earth ends in the 600s. What happens at 545-ish, give or take? The Cambrian explosion. It's when suddenly life gets interesting for the first time. As opposed to, we talk about lots of pond scum, we got little evidence of stuff going on as far back as 600. But the same things with the continents being in position, the climate finally gets good, the oxygen levels in the atmosphere are finally good enough that you could actually start to put a skeleton on yourself and not have to worry about not being able to breathe anymore. And once you have hard parts on yourself, plus with all the glaciation, the ocean's loaded up with calcium carbonate, you can make your hard skeletons out of it, you get them just floating there. And then suddenly you have preservation potential. Before that, life's probably around. We see traces of it, we see little signs of multicellular life, but we need those hard parts to really make them preservable. So that's the great unconformity. The creationists say this is the beginning of the flood. So,
yeah, that's a question about unconformity. So, are there other places on the planet where we can see evidence of that lost illusion?
Yeah. Some places in China. It really is an amazing thing. Well, lost billion years. Here, we're looking at a billion years missing, but if we went up where it contacts, say, the docks or even the Shuars of rocks, which we don't have a place to see, you're only missing maybe 300 million years. But around the world, globally, we have very little rock from that snowball era. We have like the end of snowball cycles. We have some very distinct deposits in places that involve glacial conglomerates capped by fan-shaped dolomite deposits.
So that's basically,
yeah.
Glaciation.
Yeah. And those are our snowball cycle rock sets. We have some limestones, but really very little. We're missing that about we don't have a lot from 900 to 690. 690 to present is pretty good. We have the snowball sets in there, which took people a long time to figure out. Snowball Earth is another example of somebody makes this observation about glacial deposits in equatorial rocks. I was like, no. You'd have to freeze the whole Earth over.
First time I heard that, I thought there was a real nutcase out there writing papers.
But by the but late 1990s, early 2000s, that was accepted, though the original thoughts about it went back to the...
Can you say that again, what they were speaking until 2000?
Prior to that, some people postulated impact, that these glaciers deposit a very unique kind of deposit we call a till, which is this chaotic mass of rounded boulders and cobbles and rocks of, and there are technical definitions of what is a boulder, what is a cobble, what is gravel, what is sand. That involves average diameters of so many pieces of the sediment, but regardless of which, they're a whole mixture of rocks and it's all jumbled up in a very distinct pattern. Then you have a very typical thing we call a glacial marine. And that's where you have thin layers of like muds that you see of oceans, like shales, but sitting in these things we call drop stones. And these big boulders got punched into it, and they actually have little craters around them where they were dropped as the glacier floats out over water, it melts, lets one go plunk, splats into the bottom of the clay, the fine clays. And so some people postulated that meteorite impacts could actually cause things that looked like tills. Some people thought that continental positions weren't correct. Eventually, once people really understood what was called the carbonate cap deposits, this very unique set, that's a snowball cycle, caused by, as you come out of the snowball, you start to melt that ice. Now you have less warmer oceans, but now you have a ton of CO2 in the atmosphere, so you cycle into hyperglobal warming, and you have what's called a freeze-fry cycle. But once you melt all the ice off, it gets really warm, and you melt all the ice. What does warm air do with lots of powdered rock? It goes into chemical weathering, which sucks CO2 out of the atmosphere and dumps into the oceans as calcium and bicarbonate, which then enabled the oceans to be supercharged with calcium carbonate. They were warm, and then you started to precipitate dolomite and calcium carbonate directly so fast that it made these fan-shaped crystals, which dolomite will grow. And you have these neat fans in the deposits, which are like 10, and some of them big, like 6, 7 feet tall. Really impressive. And it was that stuff, was the document of that stuff in Africa that really kind of convinced people Africa and Australia were some of those good cycle deposits are. Because Africa and Australia is the only place you can go in the world that's been more stable geologically than like the Colorado Plateau. So we're the third most stable place on the planet, certainly the only one that most of us will ever be able to most people will ever be able to get to. So that's what you're dealing with, the missing time.
Yes, and as the creationists would point out, there is no place on the planet where you have a complete sequence of geological strata.